Last time, one input gave us one slope, but a model has millions of knobs. So, how do we find the downhill direction when there are millions of directions at once? Imagine standing on a real landscape, not a curve, a surface with hills and valleys. Face north and feel the slope. Face east and feel a different slope. Each compass direction has its own steepness. Picking one direction and measuring is a partial derivative. Do that for every axis, north, south, east, west, and you've measured the slope along each. The natural thing is to bundle those slopes into one arrow. That arrow is the gradient. The gradient is the vector of all partial derivatives. Its magic property, it points in the direction of steepest ascent, and its length is how steep. The slope in any other direction is just the gradient dotted with that direction. So to go downhill, to minimize loss, you step along the negative gradient. This is the whole of training. The loss surface sits over the weight space. Its gradient with respect to every weight is one giant arrow, and each optimizer step nudges the weights along its negative. The Jacobian generalizes this to vector outputs. The Hessian, the curvature, helps fancier optimizers. Here's the whole thing in one file. We take a bowl-shaped loss in two variables, compute its gradient at a point, and show it points straight up the steepest slope on a contour map. We define fxy x squared plus y squared, a perfect bowl. We write its exact gradient, 2x in x, 2y in y. We pick the point 1 by 2 and evaluate the gradient there. We confirm each partial numerically with a tiny nudge, matching the exact 2 by 4. We draw contour rings of the bowl and plot the gradient arrow at the point. It points radially outward, perpendicular to the rings, exactly steepest ascent. That arrow is the compass of all learning, but a network stacks functions deep inside each other. Next, the chain rule, how that gradient flows back through every layer.